the second session of lectures about multiplicity theory. In the first lecture, we saw the concept of Hilbert function, Hilbert series, and the concept of multiplicity, and we saw that how we can read multiplicity either from the Hilbert polynomial or from the Hilbert series of a module. So today we are going to extend this concept. The definition that you saw yesterday was for a module over a standard graded, finitely generated standard graded ring. Today we want to extend this concept, the concept of multiplicity, over finitely, for finitely generated modules over local rings. So because here there is no grading, we should pass to the associated graded module of M. So what I'm going to tell today is that we will see the concept of multiplicity of a module with respect to an ideal, both for modules over local rings and modules over standard graded K-algebras. Also, we will see the concept of Euler characteristic of the causal homology, and our goal is to find out that how these two invariants of the module are related to each other. So let's start with the definition of multiplicity for modules over local rings. So I start with a local ring R and M, which is Noetherian. And M is a finitely generated R module. So as I told you, to define multiplicity of this module, we should pass to the associated graded module of M to have a module with graded structure. So suppose that GRM be the associated graded module of M. When M is finitely generated over R, this module is a graded, finitely generated, graded module over the associated graded ring with respect to the maximal ideal. And this ring is in fact standard graded because it's generated by degree 1 homogeneous elements. So what we did yesterday, we can apply to this module over this standard graded ring. So we can define multiplicity of M just as the multiplicity of the associated graded module. So this is how we define multiplicity for non-graded local rings. So we can go further and define multiplicity with respect to an ideal such that this multiplicity will be respect to the maximal ideal. But to be able to do this, we should have some condition on our ideal because we want to have the Hilbert function and Hilbert series. So the lengths of these graded pieces should be finite. And to have this condition, we should consider ideals with this property that you will see in this definition. So we call an ideal I contained in the maximal ideal we call it an ideal of definition of M. Whenever we have this inclusion, there exists a positive integer n such that some power of the maximal ideal times or module is contained in I times M. So, as I told you, the reason of this definition and this condition is that for the associated graded module of M with respect to the ideal I, these graded pieces have finite lengths. Then we are able to define the Hilbert function. So, for such ideals, it can be easily seen that if I is an ideal of definition of M, then all these lengths are finite. Why? Because of this condition, we know that some power of the maximal ideal annihilates this quotient module. And because this module is also finitely generated and is annihilated by a power of maximal ideal, so it has finite lengths. So this is exactly the Hilbert function of the associated graded module of M with respect to I. So we can define the multiplicity of M with respect to such ideals, which here you will see the definition. So the multiplicity of M with respect to the ideal I is just so we show it by E of I and M. This shows that the multiplicity is with respect to I. This is just the multiplicity of the associated graded module of M with respect to I. And as I told you, in this case, it makes sense because all these pieces, which are the graded pieces of this graded module, have finite lengths. So the multiplicity that we have here is just multiplicity with respect to the maximal ideal. So just note that multiplicity of M is multiplicity of M with respect to the maximal ideal. Okay. Okay, like always, you can write your question in the chat box, and in the break time, also you can talk and ask questions if needed. If you remember from yesterday, we had a description for multiplicity in terms of the first iterated Hilbert function of M. So if we just repeat it for this situation, when we have the associated graded module of M with respect to I will have a formula for multiplicity in terms of some limits. But let's see what is the first iterated Hilbert function for the associated graded module. This is called Hilbert-Samuel function, in fact. So let's, as we had before, R and M be a Noetherian local ring. M a finitely generated R module. And I be an ideal of definition of M. So the Hilbert-Samuel function of M with respect to I so we denote it by chi sub mi because it's it depends on both module and the ideal. This we define it just to be the first iterated Hilbert function of the associated graded module of M with respect to I. So what does it mean? By definition, this is just the sum of in N. This is just the sum of Hilbert functions of this graded module when I goes from 0 to N. But we know the degree I components of these modules. So this is just the sum of these lenses. And because length is additive on short exact sequences, this is very easy by writing some obvious short exact sequences that this is just the length of M mod In plus 1M. So the Hilbert-Samuel function is just this length by definition. So by what we had yesterday, the formula for multiplicity in terms of the first iterated Hilbert function, I can write this corollary. So I don't repeat this assumption unless otherwise the assumption changes. I assume that we have such a ring and such a module. In the first part, we know that chi mi is of polynomial type. Of degree d equal to the dimension of our module. And multiplicity of m with respect to I is just this limit Why? Because this is just the first iterated Hilbert function, and yesterday we saw that the first iterated Hilbert function is of polynomial type of degree of the dimension of the module. But which module? Our graded module is associated graded module of m with respect to I, but this module has the same dimension as the module m itself. So for the first part, we just use the fact that the dimension of the associated graded module of m with respect to I is just the dimension of the module. So this is why we have a polynomial of degree exactly dimension of the module. And the second part is just what we replace here. I mean, we replace the first iterated Hilbert function by this length. So this is not a new result, it's just translation of the formula for multiplicity for the associated graded module of m with respect to I. So what we want to do now is to extend this concept of multiplicity of a module with respect to an ideal to any, not just for local rings, but for any positively graded K-algebra. So we just define this multiplicity in the same way that we have here. So here we start with a finitely generated, positively graded K-algebra, where K is a field. So for an ideal, with this assumption, as we discussed also yesterday, R has only one graded maximal ideal, a unique graded maximal ideal, which we denoted again by M. So here when I say M, okay, let's write it. Let M be just generated by positive degrees, which I mean be the unique graded maximal ideal of R, and I be an ideal of definition of M, which here, I mean the same definition we have here, just the maximal ideal replaces by this. Again, we set multiplicity of m with respect to I just as the limit that we have above. So is this definition, I mean, is it well defined or not? Because if I consider I just to be the maximal ideal itself, then we can compute in two ways multiplicity, one by this definition, and the other one that we had the formula yesterday, if you remember. This limit, but for the first iterated Hilbert function replaced by length. So what I'm going to tell you is that multiplicity, by this definition, is this limit, and from yesterday's result, we have multiplicity is equal to this limit. But you can easily check that these two limits are the same. So no matter we put here length of m mod in plus 1m or the first iterated Hilbert function of m, both of them give us the same number. So this is why this definition for positively graded K-algebras is well defined. So next, what we want to do is that we want to show that for computing multiplicity with respect to some ideal, we can reduce to an ideal which is a reduction ideal of I. I mean, we can replace our ideal I by another ideal J, which is a reduction ideal of I with respect to the maximal ideal. So let's recall what does it mean to be a reduction ideal of I. So for any Noetherian ring, and the finitely generated R module M, suppose that we have two ideals J and I, such that J is included in I. We say that J is a reduction ideal of I with respect to the module M. Whenever there exists a positive integer n such that in plus 1m is equal to j in m. So 1 power of I here can be replaced by j, which is a smaller ideal. So if for some n this happens, for larger than this n also this equality holds. Just it's enough to multiply both sides by any power of n. So from some power on, we can replace this submodule by j times INM. So what we want to show is that when we have a reduction ideal of I with respect to m, then these two ideals, I mean the multiplicity of m with respect to these two ideals is the same. So to compute the multiplicity, we can just replace I by some reduction ideal of it. So this is what we want to show, which is in fact easy from the definitions. So let's I be an ideal of definition of M, and J be a reduction ideal of I, with respect to our module M. Then first of all, J itself is also an ideal of definition of M. And also both multiplicities with respect to I and j are equal. So okay, first we want to show that J is also an ideal of definition of M. So we use our assumption that I is an ideal of definition of M. This means that there exists some power n such that power of maximal ideal times M is contained in IM. And by definition, when J is a reduction ideal of M, there exists some M, some positive integer M, such that IM plus 1 M is equal to J IM times M. So we just need to prove that some power of maximal ideal times M is included in Jm. This is easy. Let me change this because now we have a lot of M here. Let's say call this R. So from this inclusion, I will have M times NRM. If I use repeatedly this inclusion, I will get this is contained. I need this power because here I want to get IR plus 1 M. And this is just J times IRM, and this is obviously contained in Jm. So there is a power of maximal ideal that times M is included in Jm. So J is an ideal of definition of M as well. Now we want to show that these two multiplicities here are equal. I just use the definition in terms of the limit. So by the definition, I have multiplicity is equal to this limit. So I want to compare this, find some inequalities between these lenses when I changes to J. We have IN plus R times M. If you consider this equality here, I can write this as I times N, J to the power N, I to the power R, M. By this equality, I have this equality. So this is contained in J and M. And obviously, because J is contained in I, J to the N times M is contained in I to the N times M. So I will have this inequality for the lenses. And if I just, multiply by this fraction and take limits, these two limits give me the multiplicity of M with respect to I, and this gives me multiplicity with respect to J. So easily I will get this equality. So to compute the multiplicity, we always can reduce to a reduction of the ideal. Okay. Now that we understood about this, now we want to find an equivalent condition for an ideal J to be a reduction ideal of I, because this is important to compute multiplicity. So I just remind for a module over a Noetherian ring, what is the Ries ring and what is the Ries module of with respect to some ideal. So let R be a Noetherian ring. And M be a finitely generated R module. And I be an ideal in R. Then remind that the Ries ring of I is just this graded module. And the Ries module of M with respect to I, sorry, this is a graded ring and this is a graded module over this graded ring. And obviously, when M is finitely generated, R module, this module is finitely generated graded module over the Ries ring. So we want to find a condition on this module equivalent to say that an ideal J is a reduction ideal I. This is the statement of our next proposition. So my assumption is like this. And of course, because I want to have an ideal of definition of M, I should consider okay, two ideals in R. And M, of course, is a module over this ring. Then the following conditions are equivalent. J is a reduction ideal of I with respect to M. This is equivalent to say that this module is finitely generated over the Ries ring of J. So to check that an ideal is a reduction ideal of I, we just need to check that this module is finitely generated over this ring. So let's see the proof. Okay, suppose that J is a reduction ideal of I, which by definition it means that for some positive integer n, I will have this equality. Okay, so we want to show that the Ries module is finitely generated over Rj. Looking at the RIS module, if we consider the high degrees, I mean the components of degree n+1 and larger, so for any k greater than or equal to n+1, I can write ik times m by this equality again as j times k minus n in m. So because I mean these coefficients come from this RIS ring, this implies that the generators of just the first n powers, I mean m, im up to inm, are enough to generate the whole module. Because as you see from this equality, the higher degrees can be explained in terms of the nth degree elements. And because all of these submodules are finitely generated, we have a finite generating set for RIM. So now let's go from 2 to 1. So assumption is that this module is finitely generated. And because it is graded module, so this means that it can be generated by finitely many homogeneous elements. So let x1 up to, say, xr be some homogeneous elements in the module. Such that they generate the module. As our J module, of course. Then it can be easily see that what we are looking for, we want to show that we want to find some power n such that this equality holds. So just take n to be the maximum of degree of these xi's. It is very easy to check that when n is this number, then in plus 1m is just j times inm. Because if you take an element here and write it as a combination of these elements, which the coefficients come from Rj, I don't want to write in detail everything because my time doesn't allow, but it can be easily checked that these coefficients belong to Jin. So for such n, we have this equality, which means that J is a reduction ideal of I with respect to m. Okay. Any questions so far? So let me explain you what is our next goal. So far we understood that we can compute multiplicity of m with respect to I by the multiplicity of m with respect to some reduction of I, and we saw some equivalent condition for an ideal to be a reduction of I in terms of this Riesz module. Our next goal is to show that under some condition we can find a very nice reduction ideal for I, which is in fact a system of parameters for the module. So to be able to do this, I need to define the analytic spread of an ideal with respect to the module. So our assumption on the ring is that either a Noetherian local ring or a standard graded K algebra, where K is a field, and M be a finitely generated R module. Let I be an ideal in R. The analytic spread of I with respect to M is defined as this Krull dimension of the Riesz module over the maximal ideal time this module. So what are the graded components of this module? I will write down here. This is just sorry. This is easy to see that this is such a graded module with these components, and this also can be written as the quotient of the associated graded ring of R with respect to I. These are the same. So dimension of this module we call it the analytic spread of I with respect to M. And when our module is the ring itself, we just call it the analytic spread of I, and we write it as just lambda I. This means that the module is the ring itself. So what we want to show is that first of all, we want to find an upper bound for this number in terms of the number of generators of a reduction ideal of I. So, what time is it? 10:45. Okay. So, in this theorem, we want to show that when we have a reduction ideal of I, with respect to our module, and then mu of j which I mean the cardinality of a minimal generating set of J, is an upper bound for the analytic spread. And the important part comes here if the field K, which is just the ring mod out by the maximal ideal, is infinite, then in fact we can find a reduction ideal of I such that lambda I and M is exactly mu of J. This is very important for us, the existence of such ideal, which we will see how it helps us to find a system of parameters that we can replace by I to compute the multiplicity. So, the first part, we want to show that this is an upper bound. For what is lambda I and M? By definition, this is just the dimension of this quotient module of RIM. So from what we learned today, because J is a reduction ideal of I, RIM is finitely generated over RJ. So if I mod out by M times RIM to get this quotient module, I can consider this quotient module as RJ mod M RJ module, of course. Because M annihilates this module, and I can consider RJ mod out by some ideal which is contained in the annihilator of the module. So let's look at this quotient ring to figure out some upper bound for its dimension. So this RJ mod out by MRJ is just this graded ring and so on. So this is the isomorphic to, okay, we know that this is a standard graded because it's generated by degree 1 elements, clearly. So this is isomorphic to the quotient of polynomial ring by some kernel. So we can define a natural map from the polynomial ring to here, which is surjective, such that this R, which is the embedding dimension here, is just the dimension of this K vector space. Which is exactly mu of J. So because dimension of this ring obviously is less than or equal to dimension of this polynomial ring, which is at most R, we get this inequality. So let's go back here. I have a finitely generated module over this ring such that this ring has dimension at most mu of j. So dimension of this module as our j module is at most mu of j. But this dimension is the same as the dimension of this module as Ri module. And because Ri is an integral extension of Rj, so they have the same dimension, so I get this inequality for the analytic spread, which is just this dimension. For the second part of the theorem, the proof is long if I go through all the details, so I just give the headline of the proof, how we can find such ideal J with this property. So the assumption that we have for the second part is that K is an infinite field. So we have lambda Im, which we know that this dimension, it is the dimension of this quotient module. It is just the dimension of the ring Ri, mod out by, I call, say, L, such that this L is just the annihilator of our module. So the dimension of any module is just a dimension of ring mod out by its annihilator. So, but when you look at this module, because we know that it is annihilated by M, this means that M times Ri is contained in L, because L is just the annihilator, and M annihilates this quotient module. So this inclusion implies that this ring is standard graded. So I call this ring A because I work with this ring. What we know is that the dimension of this ring is exactly the analytic spread. I call this number D, and what we want to show is that there is a reduction ideal J of I such that mu of J is exactly D. Okay, so because we have this assumption on our field, it's infinite. By Neuter normalization theorem, I can find homogeneous elements of degree 1 in the ring A such that I call them Y1 to YD. The length of this sequence is exactly the dimension of our ring here. So homogeneous, I mean when K is infinite, we can choose them to be of degree 1. Such that if I call this a ring K Y1 up to YD B, this is a polynomial ring. over indeterminates y1 to yd, and A is a finitely generated B module. So here I just apply Neuter normalization theorem. So because I know that our module, this module, because this module is finitely generated over A, and here I have A is finitely generated as B module, I will get RIM, MRIM is in fact a finitely generated B module. So I want to find the right ideal J, which at the same time is a reduction ideal of I, and mu of J is exactly D. What is the candidate for J? Okay, we have these elements y1 to yd in A. These elements, looking at the structure of our ring A, these elements come from some elements in the ideal I. So let Z1 to ZD be some elements in I that correspond to y1 to yd under this natural map from Ri to Ri mod L. So each Zi goes to yi. And I consider J to be the ideal generated by these elements. This is exactly what we are looking for because you can easily check that the ring Rj mod MRJ. This, I'm not going to go deeply to the detail of this isomorphism, but this holds. This implies that the embedding dimension of both rings are equal. The embedding dimension of B is this polynomial ring. This is D, and the embedding dimension of this, as you can see from here, is generated by degree 1 elements, is just mu of J. So I will have D is equal to mu of J. So this is D, this is mu of J. So J has exactly, as a minimal generating set, is generated by Z1 to ZD. And this is just the analytic spread. So we found the right J such that here we have equality. And also RIM is finitely generated over Rj. Why? Because this is finitely generated over B, and B is just this quotient module. So if as this quotient module is finitely generated, also as Rj module is finitely generated. This can be seen from Nakayama lemma. So this was exactly the equivalent condition to say that J is a reduction ideal of I with respect to M. So this ideal is exactly the ideal we are looking for. It's a reduction ideal of I, and the number of its minimal, the cardinality of the minimal generating set of it is exactly the analytic spread. So I want to confirmation RIM in your explanation, you say Rees ring. No, I call this Rees module of M with respect to I. Rees ring is just, okay. ring has the structure as a ring. This is just this graded ring. And I call this Riesz module. I didn't find a name for this in the books, but I call this Riesz module because it has the structure of a module. So this is the Riesz ring, this is the Riesz module with respect to I. And both have graded structures. So it's 11, so we can have a break for 10 minutes. So what we are going to do next, now we are enough prepared to prove that under the assumption that we had in the previous theorem when k is infinite, the multiplicity of m with respect to I can be computed via the multiplicity of m with respect to a system of parameters of the module. So this is what we are going to prove now. So my ring is, as always, a Noetherian local ring or a standard graded K-algebra. And M is a finitely generated R module. So the only additional assumption I have is that our field is infinite. And I be an ideal of definition of M. What we want to show is that there exists a system of parameters, I call it X, of M, such that the ideal generated by X is a reduction ideal of I with respect to M. So if we can prove this, this in particular, as we saw before, implies that they have the same multiplicity. So multiplicity of M with respect to I is just multiplicity of M with respect to the ideal generated by this system of parameters. So under the assumption that K is infinite in the previous theorem, we saw that the analytic spread is just the mu of some nice J, which is a reduction ideal of I. So we know that there exists a reduction ideal J of I with respect to M, such that the analytic spread of I with respect to M is just mu of J. So we want to show that this system of parameters that we are looking for are just the minimal generating set of J. So first of all, because I is an ideal of definition of M, I proved in this session that when J is a reduction of I, then J is also an ideal of definition of M. So we know that J is also an ideal of definition of M. What does this mean? This means that the dimension of this quotient module is 0, because by definition of ideal of definition, this is annihilated by some power of the maximal ideal. And we saw in lecture 1 that when this dimension is 0, the number of generators of J, minimal generating set of J, I mean the cardinality, is an upper bound for the dimension. So dimension of M. This was the last theorem that we proved in lecture 1. Is less than or equal to mu of J. So I call this dimension D if we can prove that this is in fact equality. If we can prove that dimension is equality to mu of J, then J, I mean the number of cardinality of a minimal generating set of J is exactly the dimension, and this was the definition of a system of parameters. So this means that J is generated by a system of parameters, and this is exactly what we are looking for. So my goal now is to show that the other side of this inequality also true. So it is enough to show that D equal to the dimension of M is bigger than or equal to mu of J. Okay, how we do this? We use the previous theorem that we proved for analytic spread. Analytic spread, we saw that this is equal to mu of J. So it is enough to show that dimension of M is greater than or equal to the analytic spread. What was the analytic spread? By definition, it was the dimension of this quotient module. So if I show this inequality, then everything is fine. But note that this dimension is just the dimension of the associated graded module of M with respect to I. And why instead of dimension of M I consider this module? Because now both these modules have graded structure over standard graded rings. So I can use their Hilbert's polynomial, because we can read, as we saw in lecture 1, we can read the dimension of the module from its Hilbert polynomial. I mean, this is just the degree of the Hilbert polynomial plus 1. So I just compare the Hilbert functions of these two modules. So to avoid repeating this big thing, I call it just F. So the Hilbert function of F in N. I wrote down the graded components of this module. It is just the length of I n m mod out by m times I n m. And what is the Hilbert function of the associated graded module? By definition, this is the length of this degree n component of this module. So easily we can compare these two lengths. Why? Because this submodule in plus 1m is contained in m times nm. So we have this inequality for the lengths in terms. So I just write it in terms of the Hilbert function. This means that the Hilbert function of the associated graded module this is less than or equal to the Hilbert function of GRIM and N. Because of this inclusion, this length is less than or equal to this length. So Now, what we know about the degree of the, for large n, we know that this is a polynomial of degree d minus 1, because we call this dimension to be d, which is the same as this dimension. So this is of polynomial type for large n. This is a polynomial of degree d minus 1. And we also know that this is a Hilbert function. This is also for large n a polynomial. But when this is less than or equal to a polynomial of degree d minus 1, the degree of this is also at most d minus 1. But we know that the Hilbert polynomial of f is of degree dimension of f minus 1, which is just analytic spread minus 1. And as I explained you, this inequality gives me that this degree is less than or equal to d minus 1. So I will get lambda im is less than or equal to d. And this is what I was looking for. So lambda im is exactly d. And this was mu of j. So we showed that the ideal j, which was an ideal, a reduction ideal of I, has exactly d minimal generators, which this d is just a dimension of our module. So j is generated by a system of parameters. And this was what we were looking for. So from now on, we can use this theorem. When our field is infinite, we just can replace I by a system of parameters to compute the multiplicity. Okay. Now we are going to define the Euler characteristic of the causal homology and compare this invariant to the multiplicity of module with respect to ideal, which is the main result of this lecture. This is the famous Serre's theorem, which relates these two invariants. To be able to define the Euler characteristic, I need to define what is a multiplicity system. So as usual, R is either a Noetherian local ring or standard graded K algebra. And M if a finitely generated R module. Okay. We call a sequence x1 up to xn in R is called a multiplicity system of M. Whenever the ideal generated by this sequence is an ideal of the definition of M. Or simply the dimension of m mod out by x1 times xnm is 0, or the length of this module is finite. So we consider multiplicity systems to define the Euler characteristic. First of all, let's see how multiplicity system acts on short exact sequences. I can give this as an exercise. This is really not hard to prove. Let this be a short exact sequence of finitely generated R modules. And x1 up to xn be an elements in the ring R. Then I call this sequence just by x. Then show that x is a multiplicity system of M if and only if it is a multiplicity system for both M prime and M second. So what you need to show is to show that the length of this module is finite if and only if the length of the corresponding modules for M prime and M second are finite. And as a hint, okay, just use the additivity of the lengths and by the tensoring this short exact sequence as to this ring, this I mean x is this multiplicity system, we will get a right exact sequence. Then we can compare the lengths, and we see that finiteness of the middle one is equivalent to finiteness of the others. So multiplicity system behaves well on short exact sequences. Another thing that we will use I can write it as a corollary of this exercise. Let x be this sequence x1 up to xn. Be a multiplicity system for M. Then if I consider x prime to be just the sequence that I remove x1, so from x2 to xn, this is a multiplicity system of the quotient module of M by x1m, and also for this submodule of M, the annihilator of x1 in M. This is very easy to see from this exercise. Why? Because I mean, this is a quotient module of M, and this is a submodule of M, and for both of them we have trivial short exact sequences. So if I consider this short exact sequence, because X is a multiplicity system for M, it is multiplicity system for these two both, so in particular for this. But the point is that here we want to show that X prime is a multiplicity system for this quotient module. But note that this ideal times m x1m is the same as when we consider the ideal generated by x2xn, because x1 times this module is 0, so it produces nothing. And the same for this column. We have a short exact sequence that we can compare like here. So again, x times 0 colon x1 is the same as x prime, the ideal generated by x prime times this column, because again x1 times this module is 0, so it gives me nothing. So it remains x2 up to xn. So we can replace x by x prime for these two submodules. Okay. For this part, you need to have a little background about causal homology and causal complex, because I really don't have enough time to complete material and at the same time tell about all the background needed. So I suppose you know that, what is the causal complex. So here I consider k dot x and m to be the causal complex of m with respect to the sequence x1 to xn, and the ice homology module of this complex I will denote by hi of x and m for short. So we want to define the Euler characteristic in terms of the lenses of these homologies, but first of all they should have finite lengths. If we consider our sequence x to be a multiplicity system, then we can easily see that all these homologies have finite lengths. So just an easy observation. When we have a multiplicity system of M, then all the causal homologies have finite lengths. Okay, the reason is that because we know that this length is finite. So if, because the module M is also a module over the ring R mod annihilator M, I just can replace R by R bar and assume that length of R mod X is finite. By this replacement from this, I get this. So, and another fact that I use about the causal homology is that we know that the ideal generated by this sequence annihilates the causal homologies. So what does this mean? I can consider these homologies as R mod X modules. So because the ring has finite length and this module is finitely generated, then this has also for sure finite length. So this is important for us because we want to define the Euler characteristic in terms of these lengths. So let X be a multiplicity system of M. Then the Euler characteristic of the causal homology, okay, I denote it by chi of X and M. Of the causal homology H dot xm is just defined as the alternative sum of the lengths of the homologies. And that is this sum. Okay, let this X has length n. So the causal complex also has length n, and this sum goes from 0 to n. So this we call the Euler characteristic of the causal homology. It is defined in terms of the length of causal homologies. And interesting is that it is related to multiplicity of a module with respect to I. So we need a lemma to be able to prove this correspondence. In this lemma, we prove some properties about the nature of this invariant. For example, it is well behaving on short exact sequences, like length. So under the assumption that we always have, I just write for the sequence X, which is a multiplicity system of M. We want to show that chi is additive on short exact sequences. Of our modules. Secondly, if x1 annihilates our module, then chi of x and m is 0. And we can compute whenever we have a non-zero divisor, if x1 is not in the zero divisors of M, then we can compute the Euler characteristic in terms of a shorter sequence for this quotient module, where x prime is just x, but we remove x1. So This lemma we use, these basic properties of chi we use later, especially for this nice criterion for Cohen-Macaulayness that we are interested in. So let's see very quickly this proof. All three parts can be proved easily from the basic properties that we have on the about the causal homologies. For example, for the first one, if we have a short exact sequence of modules, say m prime m m second 0, if we have such short exact sequence of our modules, we know that there is a long exact sequence of the homologies like this. And this goes up to the length of our sequence, which we consider it to be n. So because this sequence is exact, I know that the alternative sum of the lengths is 0. So I will get for each I write it down. Sorry. Minus, let's write this as a bracket, it's better, minus the length of the middle one, which is m. This is 0, so bring in mind the definition of Euler characteristic. This means that just we have this equality. Okay. So we only use the fact that there is such a long exact sequence of the causal homologies. For the second part, because I have this condition for x1, I know that, let me write down this here, I know that the homologies of x and m is equal to, here I just replace the first element in the sequence, which is x1, by 0, because x1 annihilates the module. So no matter if here in the first place I have x1 or I have 0. So I replace the sequence x by 0, x2 up to xn and m. And again, I use some long exact sequence as follows. We have such a long exact sequence of the causal homologies. Okay, I need more space, so let's go here. I use this long exact sequence. Okay, yeah, x prime and m. There is such a long exact sequence when here x prime is just x2 up to xn. So we just remove x1 here, or x1 is 0. We replace this sequence by 0, x2 to xn. So these maps are just multiplication by 0. Which means that these maps for all I are 0 maps. So what we will have, also this map is of the same kind, multiplication by 0. So this is 0. So I will get a short exact sequence of this form. So the length of the middle one is the sum of these lengths. So if I compute the alternative sum, which is exactly our Euler characteristic, and I replace this hi by the sum, I will get length of hi minus 1 plus length of hi. I from 0 to n. But here I have I minus 1, here I have I, and this is alternative sum, so all the terms cancel, and I will get 0. So this is the proof of this part, why chi is 0. And the third one, I just use this isomorphism, where when x1 is a non-zero divisor, we know that the ice homology of x and m is isomorphic to the I homology of x prime and m mod x1m, whenever x1 is a non-zero divisor. So just the alternative sum of both are the same, and we get this formula for Euler characteristic. So, sorry, hi minus 1. Okay, I have 10 minutes time. And what it remains to show for today is the theorem that we were waiting for, Serre's theorem, which relates the Euler characteristic to the multiplicity with respect to ideal. This is what the last thing that we do today. Okay, I don't repeat the assumption that R is a Noetherian local ring or a standard graded K algebra. M is finitely generated R module. So I just consider a multiplicity system of M, and I consider I to be the ideal generated by this sequence. What we want to show is that the Euler characteristic of M with respect to X is just the multiplicity of M with respect to I whenever X is a system of parameters of M and 0 otherwise. So it matters that if this ideal, this sequence is a system of parameters of M or not to get the Euler characteristic. Okay. Let's go to the proof. Let K dot be just the causal complex of x1 to xn or x with respect to n. We consider a subcomplex of K dot for any positive integer m. We consider some nice subcomplex of the causal complex, which is defined as IM Kn. Of course, when you choose an element here and maps via the causal complex, it goes to one higher power. So we consider this subcomplex of K dot. We want to show that this is, in fact, an exact sequence. Because I really should finish very soon, then maybe I don't go to the details that why this is exact. So I just write that one can show that, sorry, K dot M is in fact an exact sequence. This can be really checked easily because these maps, are the same maps that come from the causal complex. When you choose an element in the kernel, for example, in the ice place, I have this module. When I choose an element here, using Artin-Ries lemma, you can show that these elements can be written as linear combination of elements such that these coefficients come from I, and this helps us to show that these are in fact the image of something. So let's accept this, that this is an exact sequence. Then I have the short exact sequence of complexes like this. So I have a long exact sequence of homologies. So in particular, in the ice step. And here hi minus 1 of k dot m. But we say that this is exact, so both these homologies are 0. So to compute the homology hi k dot, we just enough to compute the homology of this complex. So the Euler characteristic, which is the alternative sum of the lenses of this homology, is just the alternative sum of lenses of these homologies. Okay? But what we have in the ice homology of k dot by k dot m, this is just, I mean, in the ice part, we just have the sum of m mod. If you look over how this is defined, this is just m plus n minus I m with the basis elements, say ej1 wedge eji, the basis elements that come from k dot. So the sum goes over a subsets j1 to ji as a subset of 1 to n. Because I was an ideal of definition of M, we know that all these modules have finite lengths. So we have finitely many of them because we have finitely many subsets of 1 to n of this form. So the length of it can be easily seen that when this has finite lengths, the length of the homologies is the same as the alternative sum of the, okay, let's write it down more carefully. This alternative sum is just this alternative sum, because all these homology modules have finite lengths. And we can see that what is this length, because we have n choose I basis elements. This is just the sum of the lenses of these modules. And if you remember, we had an exercise in lecture 1 that this is exactly, first of all, this length, we gave it a name today. We call it the Hilbert-Samuel function. So this is just the Hilbert-Samuel function of m computed at m plus n minus I minus 1. So if I consider this as this function, this sigma is just the difference operator delta n acting on Hilbert-Samuel function at m minus 1. So we could explain the Euler characteristic in terms of this function. But we know the nature of this function. We know that it is of polynomial type of degree d, where d is the dimension of M. So for n bigger than d, of course, this is 0. And for n equal to, let me write this here. And for n equal to d, because d is exactly the degree of this polynomial, this is delta d of this, which is exactly d factorial times the leading coefficient. So what is AD? AD is just the leading coefficient of the Hilbert-Samuel function. Okay? But again, in the first lecture, you saw that this is exactly the multiplicity. Because AD is just this limit. So this is just a multiplicity with respect to I. And when this equality happens, when n is equal to d, this means that exactly when the ideal generated by x, the x itself, the sequence x is a system of parameters of M, because n is exactly the length of this sequence, and when the length of this sequence is exactly the dimension of the module, by definition it means that is a system of parameters of M. So let me finish with an exercise that tomorrow I will use it. Okay. Let MQR be the category of finitely generated R modules with dimension at most Q. For any module in this category, we define the modified multiplicity in this form. If Q is the dimension of M, we define it just to be the multiplicity, and we define it to be 0 otherwise. What you should show is that, so we call this the modified multiplicity. Show that this is additive on short exact sequences. So if I have a short exact sequence of this form of our modules, then show that we have this equality. So I'll give you a hint. Use Serre's theorem. By Serre's theorem, we know that if this is generated by a system of parameters, this is just the Euler characteristic. And also, use the fact that the Euler characteristic is additive on short exact sequences. So we saw both proofs today, and if you apply these two, you can prove this equality. Okay, thank you very much for following.